In this section, we explain how to calculate the reaction forces. When two different action moments act on a cantilever beam. A cantilever beam is a statically determinate structure with three reaction forces and no intermediate hinges. Therefore, all reaction forces can be determined using the equilibrium conditions in three directions. For an object at rest, equilibrium in all directions must be satisfied. The cantilever beam, we will discuss, has a fixed support at point A, a free end at point B, and a length of L, as shown in the figure. We will determine the reaction forces when the action moments, MC and MB, which differ in magnitude and direction, act at points C and B, respectively, as shown in the figure. Steps for determining reaction forces. Step 1. Create a free body diagram of the reaction forces. Step 2. Determine all the reaction forces by applying force equilibrium in the three directions. Step 1. Create a free body diagram of the reaction forces. For a beam, a free end allows movement in all directions, vertical, horizontal, and rotational. A roller support allows the beam to move freely in the horizontal and rotational directions, but restricts movement in the vertical direction. A hinge support allows the beam to rotate freely, but restricts movement in both the vertical and horizontal directions. A fixed support restricts movement of the beam in all directions, vertical, horizontal, and rotational. The fixed support at point A restrains vertical, horizontal, and rotational movements of the beam, so the reaction forces at point A are the vertical reaction force VA, which restrains vertical movement, the horizontal reaction force HA, which restrains horizontal movement, and the reaction moment MA, which restrains rotational movement. The free end, at point B, allows for movement in all directions, so there are no reaction forces at point B. The directions of the reaction forces are assumed as follows. VA is upward, HA is rightward, and MA is counterclockwise, as shown in the figure. Note that the symbol for the reaction moment, shown in the free body diagram, uses the same notation, M, as that for an action moment. Therefore, it is necessary to analyze whether the M symbol in the free body diagram represents an action moment or a reaction moment, and to proceed with the analysis of force equilibrium and other related analyses accordingly. Step 2. Determine all the reaction forces by applying force equilibrium in the three directions. The unit of a moment is not Newton, but Newton meter. Therefore, moments cannot be summed with translational forces, which have units of newtons. A moment is a quantity that is not considered in the equilibrium of translational forces. In other words, a moment does not affect translational motion, but only affects rotational motion. We will now analyze the equilibrium of forces in the vertical direction. Refer to the free body diagram of the reaction forces for the vertical forces. The only vertical force is the reaction force VA at point A. Since the reaction force VA is the only vertical force, the equilibrium equation can be expressed as follows. We will now analyze the equilibrium of forces in the horizontal direction. Refer to the free body diagram of the reaction forces for the horizontal forces. The only horizontal force is the reaction force HA at point A. Since the reaction force HA is the only horizontal force, the equilibrium equation can be expressed as follows. We will now analyze the rotational equilibrium of moments. First, examine the lines of action for all forces. The lines of action are as follows. The line of action for the reaction force VA, and the line of action for the reaction force HA. To determine the magnitude and direction of the moment caused by a translational force, it is necessary to have information about the arm length relative to the center of rotation, which is calculated from the force's line of action. In contrast, the reaction moment MA, and the action moments MC and MB, in the figure, already have their magnitudes, defined as MA, MC, and MB, and their directions, defined as counterclockwise, clockwise, and counterclockwise, respectively. Therefore, the concepts of line of action and arm length are not necessary for these moments. Next, select the center of rotation. Choosing the point through which as many lines of action of the unknown reaction forces pass as possible will simplify the calculations for determining these reaction forces. In this case, we will select point A, through which the lines of action of the unknown forces VA and HA pass as the center of rotation. Then, calculate the shortest distance from each line of action to the center of rotation at point A. This shortest distance will serve as the moment arm length for each force relative to the center of rotation. Since the line of action for the reaction force VA passes through point A, the arm length is 0. Similarly, the line of action for the reaction force HA also passes through point A, so its arm length is 0. We will derive the equilibrium equation for these moments. In the summation of moments, clockwise moments are considered positive. The center of rotation is point A. Let's clarify this. Since the arm length of the reaction force VA, with respect to the center of rotation, is 0, its contribution is 0. Similarly, since the arm length of the reaction force HA, with respect to the center of rotation, is 0, its contribution is 0. The reaction moment MA acts counterclockwise, so it contributes minus MA. The action moment MC acts clockwise, so it contributes plus MC. The action moment MB acts counterclockwise, so it contributes minus MB. To achieve equilibrium of moments, the algebraic sum must be 0. This concludes the discussion on the moments. The reaction forces, VA, HA, and MA, are determined through the equilibrium of forces in three directions as follows. The signs of these forces are based on the free body diagram shown on the left. The positive sign indicates that the reaction force acts in the same direction as the vector assumed in the free body diagram. The negative sign indicates that the reaction force acts in the opposite direction to the vector assumed in the free body diagram. As evident from the calculated result of the reaction moment MA, the sign of the reaction moment changes depending on the relative magnitudes of the action moments, MC and MB. Consequently, the direction of the reaction moment MA will be as follows. Based on the relative magnitudes of the action moments MC and MB,